1 molar solution of HCl was electrolyzed using inert electrodes. Assume that all oxidations and reductions occur at their standard potentials, no overvoltage. Write the oxidation half reaction, the reduction half reaction, the overall potential for the electrolysis, and the minimum voltage that must be applied to make the electrolysis occur. Okay, so now we're talking about electrolysis. We're still using this standard reduction potential table, but now in a slightly different way. So, and first, whenever you're doing electrolysis, the cell potential will be negative. And that means that there is no spontaneous redox reaction. And in fact, for electrolytic cells or electrolysis cells, so in order to make anything happen, you must apply a voltage. Usually from a power source, but so that's going to be part of our answer here. So, and just like for voltaic cells, we're going to do these problems by noting the materials that we have and then looking at the SRP table to see which half reactions we can do. And it says we have a 1 molar solution of HCl. We know that HCl is a strong acid, that it breaks down 100% into 1 molar hydrogen ions plus 1 molar chloride ions. So we can look for H plus and Cl minus on our SRP table. This is molar, which means it's an aqueous solution. That means we also have water. And we'll look for water too, and we'll see what reactions we can do. Okay, so those are our materials. And sort of, it's just like voltaic cells. Find what you have and then find what reactions you can do with it. Now, let's take a close-up of our SRP table. And as we do, let's look for reactions that involve water, hydrogen ion, H+, and chloride ion, Cl-. Well, I've got H+ and H2O, but I don't have any of the other things, so I can't do these in either direction. I have Cl-. That means I can do this reaction in the reverse direction, meaning I can flip reactants and products and change the sign. So I'm going to make a little asterisk right here because we can do this in the reverse direction. Here's another one. We have H2O liquid. We can do this in the reverse direction as well. Keep going, da-da-da-da-da-da, all the way down here. And it turns out, our next one is right here, H+. We can do this one since we have H+ in the forward direction. And keep going. Here's one with water. We can do it in the forward direction as well. Those are the 4 reactions that we can do. Notice that this one is negative because it's forward. This one, not negative, but not positive either. That's 0. And these two, since they're reversed, they will be negative as well. And that's typically how it is for electrolysis reactions. I'm going to write all these out now. For well, let's start with our reductions. Let's start with our reductions. Those are the ones we can do in the forward direction. Take 2 hydrogen ions plus 2 electrons, you get H2 gas. That's at 0 volts. The other possibility is 2 H2O liquid plus 2 electrons goes to H2 gas plus 2 hydroxides. And this one is minus 0.83 volts. Minus 0.83 volts. Our two oxidations are going to be the two that we're doing in reverse. 2 chloride ions goes to Cl2 gas plus 2 electrons at minus 1.36 volts, and 2 H2O liquid goes to O2 gas plus 4 hydrogen ions plus 4 electrons. At minus 1.23 volts. So all I've done is I've just written the possible reactions we have. For electrolysis, even though we're going to end up with a negative, you still want to pick the most positive or closest to positive, which means that we're going to pick, of the 2 possible oxidations that we can do, we're going to do the one that's closer to positive. Minus 1.23 is closer to positive than minus 1.36. And of these two, 0 is closer to positive than minus 0.83. So these are going to be the 2 reactions that we're going to do. Let's see. So write the oxidation half reaction, check. The reduction half reaction, check. The overall potential for the electrolysis and the minimum voltage that must be applied to make the electrolysis occur. Well, the overall potential is, again, we're just going to do the same thing as for voltaic cells. We're going to add these up. This time we get minus 1.23 volts. And then the minimum voltage that must be applied. So how am I going to designate this? So usually I designate this as E sub power source has to be greater than or equal to 1.24 volts. So that's going to be the voltage that must be applied. I guess we could also call it applied. And the reason it has to be greater than or equal to 1.24 volts is that when we apply it, it will reverse, it'll make the sum of these two positive. Because for something to occur spontaneously, the overall process must be positive, even if one part is negative. Any questions so far? Okay, so we haven't done B yet. Now it's time to draw this thing. And for that, I'm going to get a piece of paper. Now, electrolysis cells all occur in the same beaker. So electrolysis just has one beaker. It has some solution. It still has 2 electrodes. And instead of the light bulb, it now needs a power source. And this is a sketch of a car battery. You can also call it a power source. But what you want is you want your 2 electrodes in your electrolytic cell hooked up to the leads of a car battery. And I'm going to do it just like I always do, so that my electrons are coming from this side and going to this side. It doesn't have to be like that, but it helps me stay organized. That means that my oxidation is over here and my reduction will be over here. Because oxidation for electrolytic cells, electrolysis cells, still means lose electrons. And it's at this point that I would like to just mention that I have not mentioned anode or cathode or the charges for those the whole time I've been talking about this. I will not ask you about them. Sure, those are good terms to know, but they will not be on the exam. I'm happy to talk about them too after I solve this problem. Okay. This, what I have here, is a generic electrolysis cell. Meaning I haven't put any personalization for the half reactions on it. Now let's add our half reactions. Let me slide this down a little bit. Our half reactions are going to be, well, our oxidation is going to take 2 waters, turn them into oxygen and hydrogen ions, plus 4 electrons. So let's see. So first off, this is 1 more HCl. That's from the problem statement. And, so my 2 materials are just going to be platinum. They're platinum electrodes. Remember, platinum is inert. Meaning it does not react. And our reactions need water to occur, and they need hydrogen ions to occur. That's it. So there's no reason why either of these has to be anything else. And platinum or carbon solid, which is graphite, are always good choices for these. All right, so now let's take our 2 H2Os. Our 2 H2Os are going to make oxygen and 4 hydrogen ions and lose 4 electrons. So my 4 electrons go up here, and my 4 electrons are going to go through the wire. And then my products are going to be O2. And since O2 is a gas, you can draw bubbles. And plus 4H plus. So it's going to get even more acidic in here that I'm making more H pluses. pH will go down, and we could measure it. Now I'm going to do one other color here for my other half reaction. In my other half reaction, 2 hydrogen ions are teaming up with 2 electrons to make hydrogen gas. Two hydrogen ions plus 2 electrons. And these arrows, by the way, same thing we did before. So in order for this reaction to occur, the H2O molecules must come up and literally, there's that word again, touch the platinum, where the electrons are stripped off or produced. And then the electrons are on this platinum, so the hydrogen ions have to come up to the platinum electrode and then the hydrogen is produced at the platinum electrode. And here come the bubbles of hydrogen. Now, these can occur in the same beaker because there's nothing spontaneous here. The battery or the power source is what's making this happen. And let's see. We drew the electrolysis cell. We drew the beaker, the two electrodes, including the material from which they're made, the battery, and the half reactions drawn where they occur. That's what these arrows means, and they are occurring at the electrodes. And it doesn't say it, but the last thing we need is just going to put for this power supply, it has to be greater than or equal to 1.24 volts. That is a lovely, complete picture of an electrolysis cell. Any questions about it?
So in mine it has zinc iodine. Would that mean that I would need to make the zinc solid the first plate?
Ah, good question. So your solution, I think you said, Zeldin, was ZnI2?
Yeah.
Yeah. So you have Zn2 plus ions and I minus ions, right?
Yes.
So, but your question, to do any of the reactions, you actually don't want zinc there because zinc would have a positive potential reaction to be oxidized. So
Okay.
this choice of platinum or carbon solid, which will be graphite, in fact, if you put zinc in there, it could mess up your electrolysis cell.
Okay. So
Yeah.
when I did mine, the zinc was the more positive for the oxidation.
That's
I don't
right.
have the zinc. So how does that work for a zinc solid going into, well, the zinc aqueous going into zinc solid, I guess?
Oh, yeah, good question. So so here where you, let's see, zinc solid. Oh, this will be over on this side, right? Because this will be the reduction. So zinc ions will be going to zinc solid. Is that what you got?
I thought the reduction was the iodine.
Well, so here's where it gets tricky. So these are these and water, because you still have water around, right?
Mm-hmm.
Are the only things that you can have besides electrons on the reactant side.
Okay.
Because those are the only reactants you have. And I know that's tricky, but that's like before when we had, let's see, when I go back to the voltaic cell, there was one that had zinc, right? We had zinc, right? So we could do zinc as a reactant. Now we can only do zinc ions as a reactant and H2O. So I would guess, right, we don't have any H plus, you don't have any H plus in your problem, so you can't do the H plus reactions.
No.
So
I just did the redux of the water to H2O plus the 2 electrons.
Right, so you can do these two for reductions, right?
Okay, so the zinc would be the reduction for this one?
The zinc ion will be reduced.
Okay, so I have the zinc and the iodine flipped.
Right. Do you know, does it make sense why?
Not really.
It's, no, it's a, so you don't have this, the zinc solid, right?
No.
So the only, like, you start down here, but you're going up this list, or you're going down the list, I guess, and you're looking for reactions that you can do. You have this, you have this. So that means you can do these only as written.
Okay. So I have to flip that.
And another tricky thing to think about too is if you're doing electrolysis, and I will, for your exam, tell you, you should expect typically all of them are negative, because that's how electrolysis works. This is actually, if for zinc, this is a reasonable way to make zinc, and that, you know, this is how they make metals from minerals. This is part of the process anyway. And so you could make zinc, you can make aluminum, and then make aluminum into aluminum foil, right? So like electrolysis is actually a powerful tool for making pure and purified metals from ions in solution. Now we look at up here. So for your iodide, you'll be possibly oxidizing your iodide at a negative 0.54 volts. Right? And so that's why part of the trickiness of this is you can only do reactions where you have the reactants. And to show that, sometimes you have to reverse, or oftentimes you have to reverse the reactions from the way they're written. Tell you what, think on that for a little bit, Selden. We'll do a little bit more, and then we can come back to it. I'm more than happy to.
Thank you.
Yeah. Any other questions about electrolysis? Okay. Oh, there's more problems here somewhere. There we go. 2 more problems to be precise. I mean, what's, oh,